We come across very often the term efficiency in antenna theory, like in antenna efficiency, radiation efficiency, beam efficiency, aperture efficiency, etc. What is efficiency? It is the ratio output to input, output power to input power. It pertains to devices, their performance. It takes into account the losses that takes place when the device is functioning. With these few aspects of efficiency in mind, we proceed to understand the terms like antenna efficiency, radiation efficiency, beam efficiency, aperture efficiency, etc. Right now, antenna efficiency by definition is the ratio of total radiated power to total radiated power plus losses. Here, the losses consist of three parts: conduction losses, dielectric losses, reflection losses. Antenna structure usually employ conductors and dielectrics. The conductors in the structure are usually good conductors, not perfect conductors. Similarly, the dielectrics that are there in the structure, they are good dielectrics, not perfect dielectrics. Perfect conductor is one for which resistance is zero. Perfect dielectric is one for which resistance is infinity. As a result of usage of non-perfect conductors in the structure, certain losses takes place. These are called conductor losses or conduction losses. Dielectric losses, they occur because of usage of non-perfect dielectrics in the design of antennas, in the structure of antennas. Now, reflection losses. When a wave, traveling wave, sees a discontinuity, impedance discontinuity in its path, it gets reflected. Reflection happens at the point of discontinuity. There, certain losses takes place, the amount being dependent upon the amount of impedance mismatch. This type of losses also takes place in the antenna while it is functioning. All the three types of losses so far mentioned, they are taken into consideration while defining antenna efficiency. We come across efficiency in another quantity, radiation efficiency. By definition, it is the ratio of total radiated power to total radiated power plus conduction and dielectric losses. Here, reflection losses are excluded, not considered. There is another term which is also efficiency, aperture efficiency. By definition, it is the ratio of effective aperture to physical aperture or physical area. It depends upon the orientation, the polarization, physical aperture, and also upon several other factors pertaining to the antenna. Its value is usually considered as 0.65%. For aperture antennas like dish antennas, horn antennas, it actually indicates how effectively the aperture, the opening of the antenna is being used to capture the incoming wave or signal. Beam efficiency is another quantity we come across frequently in the study of antennas. By definition, it is the ratio of main lobe beam area to total beam area. Radiation pattern of an antenna in general consists of a large lobe called main lobe, principal lobe, along with several side lobes and a back lobe. Principal lobe or main lobe is one which contains direction of maximum radiation, and it represents flow of radiation in the desired direction. Side lobes, back lobes, they denote radiation flow in unwanted, undesired directions. Hence, main lobe represents wanted, useful, beneficial power flow, whereas side lobes denote wastage as they represent power flow in unwanted directions. Principal lobe or main lobe is associated with a certain beam area. Side lobes too are associated with certain beam area. Total beam area is principal lobe beam area plus side lobes beam area. Total beam area, therefore, consists of certain useful, beneficial part and remaining wasteful, losses part. Beam efficiency then denotes power flow in the desired directions to the total power flow out of the antenna. The numerator, which is main lobe beam area, it has to be large for beam efficiency to be large. Beam area of the side lobes has to be small. For the beam area of side lobes denote wastage, then beam efficiency becomes large. Antennas, performance indicators, series on antennas and wave propagation, lecture number 1.14. Several parameters are required, and hence several parameters are used to indicate the performance of antennas. The need for several indicators arise from the fact that functioning of antennas is based on radiation and electromagnetic phenomena, a complex and complicated happening, and also due to multiple requirements that are to be fulfilled by the antenna. It is a critical part of wireless communication system. Out of all parameters, directivity is considered to be the most significant one. This is like amplification factor for an amplifier. In the present session, we consider directivity, its definition, description, along with some more related parameters like power gain, radiation efficiency, antenna efficiency, beam solid angle, etc. Let us begin with the definition of directivity. Directivity is indicated by capital English letter D. It is defined with respect to antennas in transmitting mode. According to IEEE, directivity of antenna in a given direction is the ratio of radiation intensity in that direction from the antenna to the radiation intensity averaged over all directions. The average radiation intensity is equal to the total power radiated by the antenna divided by 4 pi. If the direction is not specified, direction of maximum radiation intensity is assumed or implied. This is the definition of directivity given by IEEE. Stated more simply, the directivity of a non-isotropic source is equal to the ratio of radiation intensity in a given direction over that of an isotropic source. Directivity is direction dependent, but in literature, directivity is almost always specified with respect to direction of maximum radiation. In this slide, a good amount of standard information is provided for directivity. Now we move a little bit into mathematical aspects of directivity. If the direction is specified, then directivity is mathematically d theta phi. Directivity in the direction specified by theta and phi is equal to u theta phi by u average. U stands for intensity, radiation intensity. So it is radiation intensity in the direction theta phi by average radiation intensity. As the average radiation intensity is the ratio of total radiated power to 4 pi, in terms of total radiated power, the directivity can be expressed as d theta phi is 4 pi into radiation intensity in the direction theta phi by total radiated power. When direction is not specified, the directivity becomes d is equal to u max by u average. Maximum radiation intensity by average radiation intensity equal to 4 pi into maximum radiation intensity by total radiated power. But we know U max, maximum radiation intensity, is maximum of R square E square by eta. E square by eta is density, power density. When it is multiplied with R square, it becomes intensity, radiation intensity. Its maximum is U max. Total radiated power PET is closed surface integral over SdA. It is also equal closed integral U d omega. Here integration is with respect to solid angle. D omega means solid angle integration. dA means integration over ordinary area. Both are equal to integral 0 to 2 pi 0 to pi E square by eta R square sin theta d phi. Now directivity becomes D is equal to 4 pi maximum of R square E square by eta integral 0 to 2 pi 0 to pi E square by eta R square sin theta d theta d phi. A little bit of cancellation happens, ultimately resulting in 4 pi into maximum of R square E square divided by integral 0 to 2 pi integral 0 to pi E square R square sin theta d phi. When the radiation field intensity E is independent of azimuth direction, directivity expression becomes much more simpler. It is D equal to 4 pi maximum of R square E square by integral 0 to 2 pi integral 0 to pi E square R square sin theta d phi equal to 4 pi maximum of R square E square divided by 2 pi 0 to pi E square R square sin theta d theta. Now integration over azimuth angle, it results in 2 pi. Of course, this is valid when E is independent of azimuth direction. Now we have D equal to 2 maximum of R square E square by 0 to pi E square R square sin theta d theta. The directivity can also be expressed in terms of radiation intensity as D is equal to 4 pi by 0 to 2 pi 0 to pi un of theta phi sin theta d phi. Un stands for normalized radiation intensity. Now we consider another parameter, maybe more useful parameter than directivity, because power gain is a more practical one than directivity. Directivity is a theoretical one, more a theoretical one, whereas power gain is a practical indicator. The absolute gain of an antenna in a given direction according to IEEE is defined as the ratio of the radiation intensity in that direction to the radiation intensity that would be obtained if the power accepted by the antenna were radiated isotropically. This is our gain according to IEEE. The radiation intensity corresponding to the isotropically radiated power is equal to power accepted or given at input by the antenna divided by 4 pi. Mathematically, power gain is absolute gain is equal to 4 pi radiation intensity over total input or accepted power equal to 4 pi u intensity in the direction theta phi by p in. Relative gain is another term. Power gain has two terms: absolute gain, relative gain. Absolute power gain, relative power gain. So far we considered absolute power gain, now relative power gain. It is defined as the ratio of power gain in given direction to power gain of a reference antenna in its reference direction. The reference antenna can be a half-wave dipole or it can be a horn antenna. Some more terms also we consider here. These terms are very much connected to directivity. Radiation efficiency, antenna efficiency. First we define these two terms, indicators, performance indicators of an antenna. The radiation efficiency epsilon CD of the antenna is the ratio of total radiated power to the total input power. It is also the ratio of gain to directivity in the given direction. Here, the connection between radiation efficiency and directivity is given. The connection between radiation efficiency and gain is also given. Epsilon CD is equal to, mathematically, total radiated power TRP over TRP plus conduction plus dielectric losses. If reflection losses are also considered in addition to conduction and dielectric losses, then efficiency is called antenna efficiency, epsilon naught, is equal to total radiated power TRP over power incident on the antenna terminal. In this slide, we can have good amount of information which connects radiation efficiency with the gain, with the directivity, with the antenna efficiency too. The interconnection between various quantities so far discussed connected to directivity, they are shown, illustrated here in the form of a diagram: antenna, power gain, directivity, radiation efficiency, antenna efficiency. Directivity is 4 pi times maximum radiation intensity to total radiated power, whereas power gain is 4 pi times radiation intensity by total input or accepted power. This is absolute gain. Radiation efficiency is total radiated power TRP over TRP plus conduction plus dielectric losses. Antenna efficiency is total radiated power over power incident on antenna terminal. With this diagram, comparison becomes quite easy. Understanding the connection between directivity, power gain, radiation efficiency, antenna efficiency, it becomes simple, easy to understand. Another quantity, effective radiated power, it is introduced here. The effective radiated power, ERP in short, of an antenna is product of power fed to the antenna and its power gain. So ERP is input power into power gain. It is equal to 4 pi times radiation intensity. ERP is a parameter we encounter frequently in the study of antennas. So it requires to be understood about it. Another parameter which is related to directivity is considered here, that is beam solid angle. What is beam solid angle? The beam solid angle is indicated by gamma A. Sorry, it is omega A. It is a parameter that describes the relative concentration of radiation in the main beam with respect to the total radiated power. It can be defined as the solid angle through which total power radiated by the antenna would stream if the radiation intensity U theta phi is maintained at its maximum value over omega A and 0 elsewhere. This is the definition. Actually, this parameter defines an equivalent cone for which all the radiation of the actual antenna could be concentrated with the uniform intensity equal to maximum of the actual pattern. Mathematically, omega A is total radiated power by maximum radiation intensity. From this expression, mathematical expression for beam solid angle, it is quite easy to relate the beam solid angle with the directivity. We do some mathematics here. Omega A is integral 0 to 2 pi, 0 to pi e square by eta r square sin theta d theta d phi by maximum of r square e square by eta. From the definition given in the previous slide, this expression has been created. It is equal to integral 0 to 2 pi e square r square sin theta d phi by maximum of r square e square. It is equal to integral 0 to 2 pi r square e square by eta by maximum of r square e square by eta sin theta d phi equal to integral 0 to 2 pi u normalized normal theta phi sin theta d phi. Ultimately, omega A is beam solid angle is 0 to 2 pi by 2 u normal theta phi sin theta d phi steradians. Another quantity is beam efficiency. The ratio of the main beam area omega m to total beam area omega A is called beam efficiency. Mathematically, it is epsilon m is omega m by omega A. This parameter is useful to judge the ability of the antenna to discriminate between signals received through its main lobe and those through minor lobes. Interconnection is provided in this slide between beam area, directivity, effective aperture. Effective aperture is a parameter, a performance indicating parameter. It is as important as directivity, but it is defined with respect to antenna in receiving mode. Directivity is with respect to transmitting mode, whereas beam area effective area is with respect to receiving mode. Full-fledged definition will be given later. Here interconnection is provided. Directivity is maximum radiation intensity by average radiation intensity. Beam area is total radiated power by maximum radiation intensity. So these two, from their definitions, these two can be connected, and notice that product of directivity and beam area is equal to 4 pi. Later you can see that definition of effective aperture is available power from the antenna terminals by power density of the incident wave. Beam area and effective aperture, these two can be connected. Connection is AE, effective area multiplied by beam area. This product is equal to lambda square. Directivity and effective aperture, these two are also related. The relation is very popular. We come across frequently in antenna theory. AE is equal to lambda square by 4 pi into D. With this, we come to an end to the present session. In this session, the focus is mainly on directivity and certain related terms, parameters, which are also performance indicators of antennas. Notice the discussion that has been carried out in the present session, it is the most general. It is not specific to any particular type of antenna, most general. So whatever we understood in this session, that is applicable to wire antennas, that is applicable to microstrip antennas, that is applicable to small antennas, that is applicable to aperture antennas, all types of antennas. Hope this session is useful to you. We meet again in another session with a new topic soon.